Um, my name is Markus Wetzstein. I'm working for NVIDIA and PGI specifically, PGI Compiler Group. And I'm supposed to give you an overview on OpenACC, the more recent developments there and things like that. Before I get to that more technical aspect, let me spend a few words on the adoption of OpenACC. OpenACC has a growing user community. There are now about 6,000 people who have attended online training or other and are using it. There are the GPU hackathons, you might have heard of them. There's one here in Lugano in September, I believe, where application teams come get a mentor from who are knowledgeable about whatever they try to do, whether it be CUDA programming or OpenACC programming, things like that. And then they work for 1 week on their own application code and getting help with porting that or improving performance. OpenACC is also being used on Taihu Lite, currently the fastest supercomputer in the world. They've used OpenACC for their compiler technology for those chips. There are a number of commercial software packages like Gaussian for material science, ANSYS Fluent, that are using OpenACC for their development. There are a bunch of very successful implementations ranging from things like climate and weather modeling, all the way to medical imaging, various types of computational hydrodynamics and fluid dynamics, quantum chemistry, astrophysics. So it's really used across a very wide range of scientific and also industrial applications. Now, coming to PGI itself, kind of why was I tasked giving you this presentation? PGI, as part of NVIDIA, builds compilers for Fortran, C and C++. The compilers also support OpenMP and OpenACC. And PGI has been one of the drivers for getting OpenACC standardized and bringing it alive and making GPU computing possible like that. When you leave this workshop here and you want to continue with OpenACC development and you don't have a compiler available, say on your laptop or something, you can go and just download the PGI Community Edition for free from our webpage. It's a fully functional compiler suite. The only difference with our other product lines are the support is only through the user forums, and there are only 2 or 1 update a year, so it's less frequent than the other ones. But otherwise, it's a fully functional OpenACC compiler, and you can use it on any platform that you like. Coming to the compilers themselves, I thought I'd add a few slides on how to use them, pretty much as a reference sheet for you. If you're working on a Cray machine like Daint here at CSCS, then there's usually a programming environment module that you load, and then you get the compiler. You get some default version loaded through this, but you can check what other versions are available, and you can load another version. And then if you want to generate code for the GPU, you will also have to load a Cray PEXL NVIDIA module. And the XX here stands for the compute capability of the GPU that you're using. 6.0 for Pascal, for example, on Daint here. If you have that loaded, then the usual wrappers will point to the PGI compilers. If you're working on some other machine or you need to invoke the compilers directly themselves, these are the commands for them. Some useful flags are -fast gives you sort of a usually comprehensive set of optimizations for the given architecture that you're working on at that time. And another very useful flag is -minfo, which switches on compiler diagnostics. So the compiler will tell you what kind of code it generated and will tell you about problems that, for example, prevented parallelization of a given loop or give you hints how you can solve certain problems. So it's a very useful thing to check the output of the compiler, in particular when you're generating GPU code. And you can use that in an iterative way. If you want to find out things for like what does minus fast mean, for example, on a given architecture that you're working on, then you can always use the compiler with minus help and then the other option, and it will tell you what this macro minus fast, for example, expands into. Okay? When you want to build a program for GPUs, essentially you have to add a minus ACC, and then you will, all the OpenACC directives will be translated and GPU code will be generated. There is an additional flag that you probably have to use, which is minus TA, which tells the compiler for what kind of architecture you're trying to generate code. So for example, you could specify Tesla here for a GPU, and then there are sub-options that will tell the compiler what compute capability you're using. For example, if you use CC60, you get code for Pascal, and all the specific hardware things will be utilized that are on that architecture. If you're working on a, say, K20, then you would use CC35 and things like that. Similarly, you can specify which CUDA version you want to use for the code generation. Yeah?
Which one is Daint?
Daint is CC60. It's this one. That's Pascal. Similar for the CUDA version, you can specify which CUDA version you want to generate, you want to use for generating code. And then there are also other options, including this one, multi-core. That one is interesting in the sense that the compiler will use your OpenACC directives to generate parallel code, but the target platform for which it will do so is the multi-core CPU. So you get parallel code from an OpenACC source code and OpenACC directives that will execute on your multi-core CPU instead of the GPU. One question in that context is, of course, yeah, go ahead, Markus.
How does that perform? Is it just for debugging, or is it really for...
No, thank you. I was about to, that was about what I was to say. The question is, of course, what do you get if you do that? And I'll show you. This is a comparison of some of the benchmarks in the SpecXL. It's sort of a benchmark suite for accelerators. And what you see here are 3 different benchmarks. They have been compiled with Intel's OpenMP compiler for an Intel chip for Haswell. Then they have been compiled with PGI using the OpenACC directive. Some of these benchmarks have OpenMP and OpenACC. And we've used the TA equals multicore, like I just showed you, to generate parallel code for the multicore CPU. And then we've used OpenACC in a traditional way to generate code for a GPU. And this is the result that you get. You see that pretty much the baseline here is a performance on one core. It's sort of a skewed comparison. Usually for GPUs, you would do a socket-to-socket comparison. But because we need some baseline that also works for the speed up on the CPU, we're comparing it to one core. So you need to, for a socket-to-socket comparison, you need to scale down the GPU numbers to the number of cores in the socket. But what you essentially see that the code generated with Intel's compiler for their own chip is roughly about as performant as what we generate with the OpenACC directives using the PGI compiler. So it is something that you can actually use for production like that. And I mean, results vary a bit. Sometimes this is a little bit slower, faster here. Intel is a little bit faster. For this one, there's a larger difference. So, you get mixed results. It's not a sort of, you can in general expect it to be always better or always considerably slower. But depending on your application, you get something that is reasonably useful. Yeah.
So, why is there such a large difference in the 350 code there? I mean, have you an idea?
The code has a different structure for the computes. I mean, in the Spec Excel suite, there's a range of different algorithms, different ways to express the algorithms, and so on. Some of them lend themselves better to certain approaches and worse to others, and the other way around. So it's really just a mix. And we've also extended the same result, taking this benchmark, Cloverleaf, and doing that comparison on Haswell and Broadwell CPUs, as well as Power 8 CPUs from IBM, and comparing against IBM's own OpenMP compiler, and again, Intel's OpenMP compiler. And you see again that if we use OpenACC, we get roughly comparable performance. And then you can take the same source code with the same directives and compile it with -TA equal Tesla instead of multicore, and it runs on a GPU. And that the numbers are so high here, again, is a result that this baseline is for a single core. So for a socket-to-socket comparison, just divide it by roughly 10, and you get the speed up. And you see also that if you go to multiple Pascals, multiple P100s, you still get an increase in the performance. So there's still even some strong scaling there. Yeah?
So you're compiling exactly the same source code. You're just changing the compiler flag between multicore to ACC.
Yes.
And it's exactly the same code, right?
Yes. Whereas, I mean, of course, the OpenMP compilers pick up the OpenMP directives that are in the benchmark, and the OpenACC compiler picks up the OpenACC directives. But those are part of the benchmark suite, and they really have been written to be performant in both cases. And otherwise, there's no change in the source code. It's really only the compilation flag. So that just as a side note on -TA equal multicore. Coming back to the compiler itself, there's a few useful things when you use it that you should be aware about. One of them is if you want to generate some quick timings you want to know how much time a given kernel took, or you changed something in your code and you want to see if your kernel got faster or something like that. Of course, you can always go through a profiler, but if what you're looking at is a very limited amount of kernels, then you can also use this environment variable and set it to 1, and you get some timer output for those kernels that have been launched. That's sometimes a quick way to check if some improvements that you made actually improved the performance or haven't. Then, similar to the Cray compiler, there is another environment variable that you can set. It's actually a bit mask to get information about kernels that have been launched, about data transfers, about asynchronous behavior and things like that. And as I said, it's a bit mask, so you can combine it. If you set it to 1, you get the launch configurations for your kernels. If you set it to 2, you get the information about the data up and downloads to the GPU. And then if you set it to 3, you get the combination of the 2, and so on. You get it. It's just a bit mask. But it's sometimes useful to verify what's actually going on the GPU at runtime, and if that matches what you think should be going on from the way you've written the code. Another useful tool is the PGProf profiler. You can use it on the command line, and I've just listed a few examples here for reference in the slides later. It also has a visual component that is essentially the same as NVVP from NVIDIA. If you've done any CUDA profiling, you might be familiar with that. So that's a very detailed, fine-grained analysis tool that allows you to study what performance your kernels are getting on the GPU, how they are behaving relative to other kernels, choke points, and things like that. Now, coming to the more technical aspect, I thought I'd spend a few words on some OpenACC directives in the 2.0 standard that are often a little bit overlooked, and then move on to newer developments. There are some directives that if you do a first reading of like a quick reference sheet for OpenACC or something like that, that you could easily skip over and dismiss as not really useful or not really important. But then when you write something that is more than an example with just a simple loop, and you're trying to port a real-world application or some larger simulation code, these things can become very important very quickly. So it's good to have that in the back of your mind. The routines that the directives that I'm talking about are the routine, declare, and atomic directives. Routine is essentially a way to tell the compiler that a given function in your source code needs to be translated for GPU code as well. Meaning that from a compute kernel, you can call a function that still executes on the GPU. If you have an ACC parallel loop, and inside that loop you make a function call, then of course you don't want to switch back to the CPU there, and the compiler needs to have a way to know this function call, which might sit in another source file, so the compiler doesn't see it in the same scope when it's compiling your parallel loop. It needs to know, okay, this will have a GPU equivalent with certain characteristics, and it can generate code for that and then piece it together. That's essentially what the routine directive does. Routine needs to be used with gang, worker, vector, or sequential. And what that does is basically it tells the compiler this routine contains that level of parallelism in itself. I have an example here where you have a sequential routine. There are no further OpenACC parallel or kernel directives in this. And another example here where there's a vector loop inside the ACC routine, and this needs to be put into the declaration there. Okay, yeah?
Could you please explain a bit the GAN worker and the vector and sec, because the audience may not be so familiar. We just did some basic and we didn't get into what their meaning is.
If you are familiar with CUDA, then there's kind of a easy translation between the CUDA terms and the OpenACC terms. Basically, a gang is what is your block in CUDA. Worker would be a warp in CUDA. Vector is the threads within a warp, and then sequential is just a single thread. Now, of course, if you don't know CUDA, all that doesn't really mean a lot. So expressing it in other terms, you can think of vector as the pretty much like a vector lane in your CPU, where you take several pieces of data and you execute the same instruction on those pieces of data. Then worker is a set of those things that execute together, and gang would basically be the total amount of threads, if you will, that you're launching. On a GPU, these have a certain hierarchy in the sense that when you launch something, you need to tell it initially, I'm using this configuration for the gang, and there are defaults if you don't specify it. And then within those, you have certain threads and so on. And it has an impact on at what level you can do synchronizations between your threads, for example, and things like that. So it's not just a sort of useless hierarchy that otherwise has no meaning, but you have certain behavior is only possible at a certain level of parallelism and is not available on all of the levels. That's why there is some difference there. Yes?
I would have a data region. What would it be?
Data regions, okay. Yeah, do you want to repeat?
If I have a data region, maybe with some ACC loop inside?
For data regions, you would not specify these. They are only for the compute constructs. A data region only tells the compiler, move this chunk of data from the CPU memory to the GPU memory. Okay. Whereas these have to do with how you distribute a parallel loop over, like how you distribute the work elements of a parallel loop. So it's really in the
so
sharing the
does it
workload.
always refer to a loop, or?
Yeah, to ACC loop or parallel loop. And then in OpenACC 2.5, you can also use it on the kernel's construct.
But if I just have this ACC loop inside, then it will be
Yeah, then
right
this vector statement affects this loop here. It's an additional clause for the loop.
And what will happen on the left? This for loop will not be parallelized, and it will be single-threaded.
There is no work sharing here for OpenACC, right? You're not saying anything about generating a kernel or anything like that. So this function here would just execute sequentially. Every thread in the loop would just do its own piece of work without any interaction with the other threads.
But I think in our exercises we were writing it some pragma statements inside the function, but nothing, no routine.
Yes, because by default, if you just say ACC loop, parallel loop, then the compiler by default checks the dependencies and generates those loop vector and the rest.
Yeah.
So
like
this
you don't
help it.
Yes,
yeah, you don't have to specify it,
yeah.
but there are certain ways, like if you have more complicated loop nests where you might have in mind that, oh, I want to use gang parallelism on this outer level, and then I want to do some work in the gangs, and only at this other loop nest further down, I actually want to use the vector level or something like that. So it allows you to specify these more complicated things, but you don't have to. It will still work if you don't. Performance is another issue. I mean, if you have an idea for how large your loops are and how you can share things and what the dependencies are, then you can specify these in addition, and usually you can improve your performance with that. And you can look at the compiler output, both with Cray and PGI, and it will tell you for certain loop nests what it actually generated. So you can check if you haven't specified gang, worker vector, and so on. You can go back and check what the compiler did there, and then maybe you think like, well, why don't I use this here and that there instead? And then you can go in and change it.
Thank you.
Yep.
So,
sorry.
So I presume that the function fun is itself pulled from the body of another loop, all right?
Yes.
So what's the difference in the semantics of these two functions? I presume that in the left,
I'll show you that.
In the left case, the whole loop will be performed just by a single thread.
Mm-hmm. Look at this.
What will happen in the right case?
Mm-hmm. Look at this example. So here we have a parallel loop that has gang parallelism here, and it has this call to a function which we've now annotated with vec to make it more clear what it does. Then the declaration of this function contains the ACC routine vector directive telling the compiler this in itself has some more vector loops, which you see there. And then in turn, just to make it complete, inside this vector loop, there could be another function call, and this function is then sequential, like it executes in serial, if you will. And this function has been annotated with routine sequential. So this annotation of things in your call tree, in your application, allows you to put the parallelism where you want to have it, and then make sure that the compiler generates code for the GPU in those other things that you call further down in your loops.
I see. So basically this means that the parallel loop pragma also has a certain hierarchy between gang, vector, and sequential.
Yes.
That's something which we have not studied.
Okay.
Okay, now it's clear. So you can really actually increase the granularity.
Yes, you can increase the granularity down to essentially the serial level, if you will.
I see. Thank you.
Mm-hmm.
Just as an additional comment, just to make the connection with what we've said at the introduction and the CUDA blocks and threads. So the gang is like spreading the iterations of the loop across blocks, right? And then the vector is spreading their iterations across the threads of the block. more. So this just to make the connection and understand the levels of parallelism.
So vector length on the left side corresponds to the block size.
No,
Number of threads.
yeah, to the number of threads in a block, yes.
Good. What if I just want to...
What if I just want my loop to be spread over all computing units in all the blocks over the whole GPU?
You could write, for example, a gang vector, and then you get that all, basically you're mapping the parallelism of that loop that you're looking at down to the thread level, all in one go. And then if you would have any function calls in there, they would essentially be sequential like these. So every thread in your loop iteration, when it encounters that function call, would go call that function, execute what's there, and come back.
So should I say gang or should I say vector?
Gang vector.
Oh.
If you want to if you don't want to go deeper in that hierarchy afterwards, if you don't have additional inner loops that you want to map with a different parallelism.
Thank you.
What if you just say vector and don't say gang?
Then in that case, the gang level is implicit.
I see. So the number of threads per block for the
there are defaults for the numbers. Like if you don't specify there's vector length here. There's also num gangs and so on. Similar clauses where you can specify in CUDA what would be your launch configuration, like which grid size, which block size, and so on. And if you don't specify those, then the compilers will pick defaults for you.
So if you specify nothing, then perhaps you will get vector by default, or you should specify some level.
Yeah, you will. I think the default is
128, I think.
The default size is 128 if you don't specify it.
Basically, if you see in the exercise we did yesterday at OpenACC, we were compiling with minfo equals Excel, and then we were getting for each of the kernels, although we were just having ACC loop, we're getting the full specification at the output. So it was ACC loop, gang vector, vector length 120. So then you can see what the defaults exactly are and what the compiler can do.
Yeah, it's always a useful thing to go back and see what the compiler actually generated for you if you're in doubt about some defaults that have been applied.
Thank you.
JG, you had a question as well? No? Okay. The same thing, of course, exists in Fortran. In C, you've seen here your pragma goes in front of the loop here. And if you have any external declarations, it needs to be there as well. And I'll show you that in another example. In Fortran, you have the same thing. Here, the routine declaration would sit in the declaration block of your subroutine. And then you have some parallel loop which calls a routine. And the compiler knows that it needs to generate GPU code for this routine. And the call will work like that. It's exactly the same thing. Another important thing, if you're working with C++, you might very often get into the situation where the declarations for various functions that you call are, for example, in system headers. So you can't change them. You can't go into the system header and add a pragma ACC routine sequential to that by yourself, because you might not have write permissions or things like that. Also, if you're working with libraries, it might be a similar thing where you don't want to, when you switch to a new version of the library, go in and manually add those things to all the headers that you did the last time you installed the library on your system. The PGI compiler will automatically create ACC routine sequential clauses for things that you call in a parallel construct in C++. So you can still go in and for your own user code manage ACC routine as I've shown you before, but it will basically do that under the hood for just to save you the work, and sometimes you really can't do the work because you don't have access to those headers and you can't change them yourself. And in C++, this is much more common that you can think of some lambdas you're calling or some things from the system, and you can't go in and do that yourself anyways. The compiler will generate those automatically if you're using C++.
But the source code should be still available.
Yeah, I mean, you will need to, while you're compiling, you need to be able to read the headers, right? But you might not be able, either not able to in terms of access rights, or you might not want to put in the work to go into the headers yourself and add all those routine declarations for whatever little function that you're calling, right?
So they will be parallel then, those?
No, they will not be parallel. The compiler will only generate routine sequential. That means you can call it from GPU code and it will execute serially on the GPU. So sort of the most basic thing that you would need to make it actually compile, and then if you have something more tricky in mind, you might still need to express that. But essentially, if you're using a whole bunch of things from, say, the system headers or libraries that do not have those specifications, your compile step would already choke at the point where you're missing these declarations and you're making these calls from a parallel region, from an OpenACC parallel region. And that's why the compiler generates those automatically for you.
But you said that's optional, routine clause.
It is optional in the sense that, well, I should step back. It is not really optional in the sense that when you make a call from a parallel region, then the compiler will need to know that this routine actually has a GPU counterpart that it can call. And I think that's the same for Cray, right? You need to specify ACC routine if you call from a parallel region, as far as I know, right? Yeah. So as soon if you write your parallel program here and you have a call in there and you would not write pragma ACC routine vector here, you would get an error in the compile step, and the compiler, yeah, or is it auto-generated for Cray?
I thought it's auto-generated.
Okay.
I think even if you have a routine which is...
I'm not 100% sure, I have to double check, but I think even if you have a routine you call in a parallel section, but you have no additional parallel statement in there, like the last one you have there, I think the compiler realizes that it has to build a parallel version for that.
Okay. Okay, I think with PGI compiler, you will need to specify that so that it knows what to generate.
But you don't have to specify it if the function is defined in the header file.
Yes, for C++, if you're using the C++ compiler, it will auto-generate those from the header files.
So if the function is defined in the header file without the pragma, it will be generated by default as a sequential function.
In the C++ compiler,
yes,
not in the Fortran
yes,
compiler,
but
for
if
example.
the function is defined inside the main body of the source code, then the sequential version will not be generated. It's a bit controversial.
No, it will also be generated, like for C++ classes. So you have your constructors, destructors, and you have some data manipulation members inside your classes. For those, it will be generated as well.
So for C++ compiler, pragma ACC routine is optional, and by default, the device version of the function will be always generated. If
yeah,
needed.
and for your own classes, you might need other versions like ACC routine vector or something like that.
I see. Thanks.
Now another thing that often comes up when you're porting larger code bases is global data. If you look at this example, we have a declaration of some array here, and then some parallel, some loop here makes a function call into some function that is defined somewhere else, maybe in another file. Here, that global data has an extern reference, and the function then uses A inside. Now, if you want to put that on the GPU, the question is, how do you do that? I mean, all of the regular arrays are kind of trivial, and you've learned that in the workshop already. The global data is sometimes a bit more tricky because you still need to make that available on the GPU, right? So how do you get that global data on the GPU that is essentially there once you start the program? This is not something where you execute a malloc and then you have your memory space and you do a copy or copy in or something on it. The way this works is with declare create. So like before, now we have a parallel loop here. We're calling a function. The function has its own annotation, this time here on the extern declaration as well as the function itself. That's what I've just shown you before in the other example. And now the global data gets an ACC declare create of A. And that way the compiler knows that A here has a GPU counterpart. There is memory on the GPU that has been allocated for this. And it will use that. If A gets initialized somewhere before, here, of course, you might still have to invoke an update directive on it to get it over there. But the point is, if you would try to have just a data region for A there, then this reference here in your GPU routine would not resolve to a global GPU copy of A, if that makes sense. So for the global data, ACC declare create is often the way to make that work. And in Fortran, it's actually more common where you would have a module with some variables inside the module. They are global data. And if you want to make that available on the GPU, you would have to add an ACC declare create here so that there is a GPU counterpart of that data. And the transfers afterwards you manage with update directives like before. There are some more additional clauses to the declare directive, and you can look into the specification, but I think the by far most common use is declare create that you will need in normal applications. I mentioned atomic in the overview slide. Essentially, OpenACC also has an atomic directive which you can use for atomic updates on intrinsic variables. It's pretty much the same like in OpenMP. I think there are only very minor differences between the two. And then the compiler will map that, for example, on Pascal. The hardware intrinsics for atomic updates have much better performance than they had before on the K20 and other Tesla generation chips. So then whatever your atomic directive will be, depending on how you translate the code for what target architecture, it will be translated to those efficient hardware atomics. And you can use those in your code. I didn't put that on a separate slide. Let me come to unified memory. When you look at a compute node today, then essentially the physical layout is something like this. You have your GPU with its own memory, you have your CPU with its own memory, the system memory, and then you have some kind of interlink here that connects the two, be it PCI Express or NVLink if you're on a power CPU. And as you've seen in the rest of the workshop, you essentially have to take care of moving things back and forth between these two memory spaces. So wherever you're doing your compute, you have the right data available at the time, right? That's what the whole data directive business is about in the end. Unified memory essentially creates a view like this. So you see the GPU and the system memory as one unified memory. It's essentially a virtualization. And whatever you're accessing from your compute parts will be moved accordingly. I mean, remember, this is a virtualization. We're not sort of if you set the flag to use unified memory, the PCI Express magically gets ripped out of the board and somehow the GPU gets smashed into the system memory. You're not getting rid of this. But whenever you access something on one side of this or the other side, the corresponding data will still move across the bus, but from a programmer's perspective, from a developer's perspective, you don't have to explicitly specify the move anymore. You can treat it as if there is really just only one memory space and you're accessing stuff in your memory space. Okay? This actually allows to change the development for GPU programs and exploit that. So what we usually recommend when you're porting an application for GPU, and I should mention that unified memory is something that became available with CUDA 8, and starting with the Pascal architecture, there's also hardware support for migrating chunks of memory back and forth. If you try to use unified memory on older architectures, it becomes inefficient because that hardware support is not there. So you could still use CUDA 8 with unified memory on an older architecture, but the results that you're getting in terms of performance are not really that good because the hardware doesn't really fully support it. On Pascal, however, there's something that allows you to migrate pages of memory back and forth between the GPU and the CPU, and that is used by the CUDA 8 driver then and the runtime. So the way we usually now recommend porting is when you're porting with OpenACC, you would essentially first just parallelize your program. So at that step, you're caring for correctness. You want to parallelize it and hopefully still get the same answer or some that is within some reasonable tolerance for the problem that you're considering. And you would do that by specifying -t = multicore and putting in compute constructs into your code that enable the compiler to do the parallelization, right? Then in a second step, you would switch from T = multicore to T = Tesla. So now you're on a GPU target, you're generating GPU code, and the sub-option managed here gives you unified memory. So at this point, your compute construct here will be a GPU kernel. Your code will run on the GPU, but you're using unified memory. You're using this view, and you haven't specified anything in addition in your source code regarding what to move around between the memory spaces. You're treating it as if before here you have one memory space. You don't have to do anything about it. Yes?
If there was a function call inside this loop, would we also need in the offload phase to add all the clauses we saw before?
Not for the data management. Like all the compute constructs stay the same, like your ACC, parallel, and loop, and kernels, and things like that. But any ACC data is not needed.
Well, then we need to adapt the compute part of the directive.
No, you would just not specify it at this point.
Okay, okay, we just don't.
Yeah, so you wouldn't. Okay, now I understand your question. No, with your parallel loop, you would not specify copy in or present or things like that. It's essentially as if you wrote present for everything, and somehow the runtime system magically made everything present wherever you are. Okay.
Okay.
That's kind of a way to think about it.
Yesterday, that was for us kind of the situation.
No, because if you remember, we have a large data region inside. So if we haven't tried that option because it's in the compiler we use was a bit old. So I don't have the So, yeah, yesterday we didn't do that because we explicitly did the data management ourselves. You remember this large outer loop, and then inside the specific functions, we were saying, okay, AC loop present and the arrays, but we had copied the arrays before that.
But I thought somehow the very first exercise was that we didn't specify anything about the data movement, and it still worked, but slowly, and then
if you don't specify data movement, the compiler will generate implicit data movement. Like if it can find out for your loop, oh, you're using the array A, you're reading from it somewhere in your loop, and then you're changing the values, so probably you will also want the result back. Then the compiler will generate an implicit, so you haven't written down copy my array, but the compiler will generate an implicit copy, both in to bring the results in which are read, as well as out to get your results back. So if the compiler can make that determination, essentially what read and write accesses are there, it will generate those things implicitly. If you're using the data inside subroutines, then you will still need to tell the compiler to get rid of additional copies of it, for example. And you can think of some complicated structures where you do, say, a bunch of indirect addressing and pointer aliasing, where the compiler might no longer be able to find out where this piece of data that you're using actually is coming from, and are you actually manipulating it and want the result back, or are you only reading from it? So then this might not get the result. The implicitly generated data directives might not give you the result that you want.
But essentially, we were working yesterday on this.
No, yesterday I showed you two things. One was we had a step loop, and then this was calling functions. So initially I showed you that you could, instead of you were doing AC loop, p copy in or copy in, copy out in each individual of those functions, in each individual of those loops, internal loops, and then the compiler would first time copy in and then see if it's present or not and decide whether to copy in or out. And then I showed you the large data region outside, and each of those functions had the AC loop, whatever present the arrays it had. So that was the final version. Unless you're confusing with the other thing with the MPI, which was a different thing.
I was thinking about the first most exercise we did. But
with OpenACC.
Or OpenMP maybe.
I did not get completely the question. I mean, yeah, the first noise exercise we didn't specify. I mean, we just specify the kernel, so we didn't set the data scoping.
Yeah, so essentially we were in this approach.
Actually, no, because we did not specify that we want to use unified memory.
But it still worked.
Yeah, it still worked since the compiler did the data movement set implicitly by itself.
Okay, so those are two different things.
And then afterwards we override that default data movement by setting, okay, we better know, we just need to copy there or copy back, whatever. So we would use the default data movement in that sense. What we are talking about here is that we have really one big memory and do not copy forth and back.
Explicitly through
But
directives.
if I understood it correctly, you can just do it if you have CUDA managed memory, right?
You can do it with OpenACC as well. You can use OpenACC with managed memory.
Okay.
That's sort of the third step here, coming back to this example. Basically, once you have your code working in parallel on the GPU, then we do that as an optimization step, that you move away from the unified memory, you drop the managed here, and then you put in explicit data directives for where you want your transfers and your data lifetimes. And that's really kind of an optimization step on top of that then. But yeah, you can use OpenACC with unified memory.
I think. Oh.
Excuse me, can I just want to point out that's one difference between the PGI compiler and the Cray compiler. Cray compiler can also do unified memory, at least in version 8.6, but there you have to use CUDA managed memory. So you really have to specify the CUDA malloc first yourself.
Yes, this is, I think, a difference that comes from the architecture. In the past, I think up to Kepler, you had to allocate yourself CUDA managed memory and then go with unified. But now, since there is hardware support, even if you do a simple malloc, then and you try to access something from the GPU, it page faults, and then there is hardware mechanism that brings the page in, right?
Well, that you don't have to change the mallocs has nothing to do with the hardware support as such. Essentially, what the compiler does is it will replace your ordinary mallocs and allocates in Fortran with corresponding allocates in unified memory under the hood for you. And then the hardware support enables your application to move those pieces of data back and forth on a finer granularity with Pascal and CUDA 8 than before. Like you could use unified memory on, say, a K80, but essentially, if you read something from unified memory on the GPU side, you would copy everything that was allocated in unified memory over to the GPU and the same back on the CPU. So it becomes very inefficient. But that is because the hardware has no granularity where it can say, this piece of data lives on that page of memory, and all I need to do is migrate that page rather than the whole thing. Okay? So this is kind of the process that we successfully use now for many applications. It sometimes gets a little bit tricky if you have a lot of derived types, then it gets into that deep copy complexity that I'm sure Manders will have said something about as well, or you might have. And I'll spend a few more words on deep copies later. Yeah.
So far here with the compiler flags, it always seems that you need to specify the Tesla cards with that, or how much of that would also work, like say on a GTX 1080 or Titan X or something with the Pascal architecture?
That would work on a Titan X as well. The difference would be that if you want to do double precision floating point, that would not be on your sort of consumer level gaming card.
Yes, yes, yeah.
But
you have this lower ratio of
but otherwise it should work.
Okay.
So you provide
So the
fully support also for GTX?
Actually, no. With unified memory is a good point. I will have to look that up. I'm not entirely sure if the support is in the drivers for unified memory. I think that actually it is only for the Tesla compute and not for the GTX line. But I'm not entirely sure. I'd have to look it up.
Okay. Yeah. Thanks.
Of course, the question is, if you make it to this step here, so you have your program parallelized, it runs on the GPU, the question is how important is the optimization step, right? If I don't do it, do I lose a factor of 10? Or if I don't do it, do I lose 10%, right? And how much, essentially guiding you how much time should I spend on the data directives or rather not, right? And we try to quantify that by using the SpecXL benchmark. Excuse me. So these are the different tests in the SpecXL benchmark. What we've first done is we've compiled them with the data directives in there, the way they're written in the benchmark suite normally, and that's the 100% line that you see here. So all the data management is like you programmed it so far in the rest of the course, not using unified memory. And then we essentially switched to CUDA 8 unified memory, no longer using the data directives, and see how much of this 100% line can we actually recover in terms of performance. Okay? So that's the exercise here. The 2 bars that you see for every single test are the NVLink and PCIe results. So on Power 8 Plus architectures, you have NVLink, which is a slightly faster interconnect between the GPU and the CPU. And otherwise, on Intel CPUs, you have PCI Express. That's what the 2 bars are. And you see that, yeah, there is some variation, but overall, for most of the tests, you are within 10 to 15% of what you get with a fully directive-based approach. So it is really more of an optimization step and not absolutely crucial, at least for the types of codes that are contained in the SpecExcel benchmark. There are some outliers, like this one here, for example, that has within a parallel construct calls, and then there are Fortran automatic arrays that need to be allocated and deallocated all the time. And the allocations in unified memory themselves are more expensive than they are in regular memory. So that gives you a penalty there. And then there are some other anomalies here. Palm, for example, has a lot of paging where the pages migrate back and forth between the host and the device a lot because you're accessing it from both sides a lot. So while there is some variation overall, unless you have a few cases where really unified memory is not working very well because of the kind of code the data structures in the code, I meant to say, you usually end up with something in the 10–15% range of actually writing the directives yourself, which is a pretty decent result because it can save you a lot of time if you don't have to. Oops, sorry. If you don't have to. Come on. Specify the data directives. And there are cases where you really want to put them in because you want to do something more complicated, or it becomes an important optimization, and so on. So unified memory is not sort of the wonderful answer to everything that you might possibly want to do. There are use cases where it's not working so well, but there's also a very large range of use cases where it works pretty well and can actually save you a lot of work. So that about that. How am I doing on time?
Let's say 7 minutes.
Okay. Let me get to the newer versions of the OpenACC specification of the OpenACC standard. So I'll talk a little bit about the 2.5 specification, and then I'll give you an outlook on several features that will probably be in the 2.6 specification. What I'm listing here is not a sort of a complete list of all the changes relative to 2.0, but these are probably the most interesting ones, and then you can always go back to the specification, to the standard, and there's a section at the beginning that lists all the changes. But these, I think, at least are the more important ones. One thing is that with 2.5 you can specify, you can specify the numgangs, workers, and vector length clauses also on the kernel's construct, and not just on the parallel or loop construct. You've always used parallel loop?
Yeah.
Okay.
We use the parallel loop.
Okay.
Not the kernel.
There is a directive in OpenACC, which is ACC kernels, that essentially does pretty much what ACC parallel loop does, but it gives the compiler more freedom about how to create those kernels. For example, the compiler can also look at what you've done there, and it might be so complicated that it cannot make it work, and it can almost refuse to put that on the device because there are all kinds of data dependencies and things. So kernels gives the compiler some more freedom for how to generate the kernel rather than you specifying all the details. And yeah, it essentially works for most cases like parallel loop. And up to the 2.0 specification, you could only use these here on parallel loop, and now with 2.5 you can essentially specify a launch configuration also for kernels.
Thanks.
Then there are a number of new directives, init, shutdown, and set, that are essentially as APIs before, and now they're also existing as directives. So you can put, for example, an ACC init directive when you want to initialize your GPU. And there are cases where that's something, I mean, that is done anyways when you launch your compute for the first time. Like the first time you do anything on the GPU, all that initialization will be done. But depending on how you write your application, you might not want to do that at the point where you're sitting in some other large iteration loop. And you might want to pull that out for site timing purposes or things like that. Also, interoperability with OpenMP is something where you might want to do the initialization separately and make sure that they work well together. Then the update directive for transferring things back and forth that are already allocated. In the 2.0 standard, if you used update on something that at the time does not have, so you say update device variable, and that variable does not exist in the GPU memory at that point, you will usually get a runtime error because it doesn't exist, so you can't update it. In the 2.5, if present is allowed on the update as well, so you can specify that this update is essentially to be ignored if at that point of your execution there is no GPU version of that variable. Then ACC routine, we've talked about that. Those are now required to have one of those clauses, where before they were kind of optional. 2.5 also introduced a default present that can be useful. Say you have a compute construct and you want to make sure that all the data has already been copied sometime before. I mean, for a simple loop with like 10 lines, you can just look through and you know what's in there, right? But if your loop is a couple of 100 lines and it might have a couple of function calls in there, you might not want to go through the entire thing and dig out every single variable and put that into a corresponding data clause. So you can specify default present, and then you will get an error if a given variable or array is accessed inside the parallel region and it has not been copied before. So it's useful in those contexts. Then there's a pair of new API routines, get default async and set default async. I don't know how much you've talked about asynchronous queues. No? Okay. Okay, I'll be quick and then you get to them. So the API routines allow you to basically query which execution queue is used by default or set another one. And that will make more sense once you've heard about async as well. Then in OpenACC, you have these API routines and you have the directives. And usually you can express most of the things either one way or another, or both ways actually. And the API routines so far had been adding counterparts that take these asynchronous, that provide that asynchronous functionality. And in 2.5, they've been added. Then there's been an interface for profiling and tracing tools that has been specified, so that third-party tools developers like Scorpy and Tau and Scalaska and whatever is out there, that they have a standardized way how to tie into an OpenACC application. And there's a whole bunch of clarifications in the text. The other big change that is probably worth mentioning is reference counting. You probably haven't talked much about reference counting. Okay. Reference counting has been used under the hood before to manage your data, like when does data need to be copied to the GPU, or is it already there so it doesn't have to be copied anymore and so on. The 2.5 standard actually put that into the standard so that there's a common language with which you can communicate about these things. And then it also changed the behavior of the data clauses, copy, copy in, copy out, and create, to what has before been present or copy, copy in, copy out, or present or create. So if you now in 2.5 specify copy, it will behave as a present or copy before. And what that means makes more sense when you look at reference counters. And I've done a simple example here where you have a data region that contains some variable, and then you have a nested data region sometime later that specifies the same variable. Okay? Now what happens, the reference counter is essentially, actually there are two reference counters for the data directives and then the enter-exit data directives. Those are counted separately for some reason, but I won't go into the details of that. Essentially what the reference count is keeping track of how many data regions that are still active are using a given variable on the GPU, okay? So at the beginning of this here, the reference count for this variable is 0. It hasn't been used on the GPU, it doesn't exist on the GPU. When we encounter the beginning of this data region, the reference count is increased to 1, and a copy in is performed so that you have the data in that variable available on the GPU, okay? Now you have some other code, and when you reach the beginning of this data region, a check is made on the reference count. The reference count before was 1. It is always incremented when you start an additional data region, so it goes to 2. But now also, because it was already present before, and copy now means present or copy, it means that there is no additional copy in at this point. You would need to use an update directive if at this point you wanted to explicitly move data across. Because it already existed on the GPU before, this becomes a present or copy, and that means it turns into a no-op. Nothing is done. Then in this data region, you have some more compute going on, and once you reach the end of the inner data region, always at the end of a data region, there's obviously one less active data region using that variable, so the count needs to be decreased. Now it goes from 2 to 1 at this point. And because the count is still 1, there is no copy out performed for the end of this data region. It is still in use on the GPU. And then once you reach the end of the outer data region, the count is again decreased. It reaches 0, and now the runtime sees, aha, I need to copy this back because of this, and it is transferred to the CPU. So it's not something that you have to fundamentally understand for writing OpenACC code, but in more complicated regions where you have like nested data regions and so on, it can be useful as a tools for understanding what's actually going on. And it has been formalized in the 2.5 standard so that there's kind of a common language to talk about these things. Let me quickly talk about the 2.6 features, and then I'll almost be done as well. 2.6 has not been finalized yet, so there is no 2.6 standard as such. The features that are likely to be included in 2.6 are a manual deep copy will make it into the standard specification, and I'll tell you a little bit more what a manual deep copy is. And then there are, this is actually already implemented in the PGI compilers today. Like if you take a current, say, 17.4 compiler, then manual deep copy is already supported. There's a new clause, no create, for some circumstances. Then the host data directive that you might have heard about when you're doing library calls and you want to expose the device pointer for a library call so that your device library can use that without an additional transfer. That gets an if and if present clause so that you have more flexibility there. Then Fortran optional arguments will probably be standardized a bit better in terms of what is to be done with them regarding OpenACC. All the API routines will get Fortran bindings. So far, for some of them, there are only C and C++ bindings. There will be something like a serial offload region, which you can think of as you're launching a kernel with one thread that in serial does something, but it has to be on the GPU because that's where your data is. It's kind of like a shortcut to launching a ACC parallel loop numgangs 1 vector length 1 kind of thing, so that you have a shortcut directive for that, if you will. There will probably be a few more device query routines, and then also something where you can catch errors from the GPU execution. There will not be a full-fledged like exception handling thing like in C++, but it will be something where you can check if there was an error during execution, and if your large MPI application on 10,000 MPI ranks encountered an error on one GPU, you can actually gracefully exit by calling MPI abort, rather than this one rank maybe hangs or crashes and then crashes the others and so on. So there's a way where you as a user can shut down the program in a meaningful way. And then there are a number of cleanup items and so on. So that's what likely is to be in 2.6. And let me quickly, and as a last point, get to the deep copy, what that means. Pretty much in modern day applications, you no longer have very simple data structures where every data that you use is just a simple array of, say, reals or floats or whatever it might be. You have structs of arrays of structs, you have classes, you have things where you have a user-derived type here, and then inside that you might have pointers that again are of another derived type and things like that. And you can think of entire sort of tree hierarchies where this guy might as well have pointers that are of another derived type and so on. And the question is how you map this kind of thing to a given HPC architecture. Like with a GPU, you have a distinct memory space here where you have to move things across. Also on KNL, you have two different memory spaces, and it looks like programming for KNL will, to some extent, require the user application to manage how you want to use the HBM memory. So it's kind of a common problem how you deal with these complex data structures under those circumstances when you as the user have to move them around. What I meant with a manual deep copy before is essentially this. You have a type def here. You see it has a bunch of pointer members and then several members of intrinsic type that have a fixed static size. And then you have some piece of code where there's a variable of this type. And after initializing the variable and doing allocations for these pointer members, you now have some compute that is using these members, x and y and n. So somehow you need to bring your variable p of type points over to the GPU, and the question is how you do that. And that's essentially deep copy.
Let's get offline the questions because we don't have enough time.
So the way you do that, like manual deep copy means you will use an ACC data create for the actual variable that gives you the allocation on the GPU. So on the GPU, you will have space for n, you will have space for coef and direction, and you will have space for these pointers, but not for anything that they point to, only for the pointers themselves. Then once you're done setting up P, and these things actually have values and memory that they point to, you will do an update device for the things that are of an intrinsic type, like n, which is an integer, and you will do an ACC data copy in of the individual members that you intend to use on the GPU. And what this does, what manual copy does is it will give you on the GPU version of P, the pointer inside, pointing to X, will point to the memory which corresponds to X on the CPU. So you're preserving this pointer relation, and you can use your derived type here like you expect to. That's what you wrote it for in the first place. So that's what a manual deep copy looks like. You're essentially manually constructing this type on the GPU, which is of course tedious, but it is at least a solution to the problem. You can make this work, and you can manipulate individual elements of this derived type on the GPU and copy things back and forth as you need. And as I said, this works at the moment already in the PGI compiler. What everybody wants is the true deep copy, and that will be the big theme for OpenACC 3.0 standard, where now you would specify, there's a technical report that outlines a few things how this should be done. You would specify in the type which members you intend to use on the GPU, and you can specify some policies and things to give you some more freedom and flexibility about how to move that. And essentially here at the point where you want to start your compute, you only write ACC data copy of P as if it would be an int or a float. And everything else is done without you interfering, where before you needed to manually construct that type on the GPU. That is the meaning of true deep copy, and that's probably going to be the big theme for OpenACC 2.6. And with that,
so thank you, Markus.
I'm at the end.
So let's do a quick break of 5 minutes, because then we'll have like an hour of presentation.
My name is Markus Wetzstein. I'm working for NVIDIA and PGI specifically, PGI compiler group. And I'm supposed to give you an overview on OpenACC, the more recent developments there and things like that. Before I get to that more technical aspect, let me spend a few words on the adoption of OpenACC. OpenACC has a growing user community. There are now about 6,000 people who have attended online training or other and are using it. There are the GPU hackathons, you might have heard of them. There's one here in Lugano in September, I believe, where application teams come, get a mentor from who are knowledgeable about whatever they try to do, whether it be CUDA programming or OpenACC programming, things like that. And then they work for 1 week on their own application code and getting help with porting that or improving performance. OpenACC is also being used on Taihu Lite, currently the fastest supercomputer in the world. They've used OpenACC for their compiler technology for those chips. There are a number of commercial software packages like Gaussian for material science, ANSYS, Fluent, that are using OpenACC for their development. There are a bunch of very successful implementations ranging from things like climate and weather modeling all the way to medical imaging, various types of computational hydrodynamics and fluid dynamics, quantum chemistry, astrophysics. So it's really used across a very wide range of scientific and also industrial applications. Now, coming to PGI itself, kind of why was I tasked giving you this presentation? PGI, as part of NVIDIA, builds compilers for Fortran, C and C++. The compilers also support OpenMP and OpenACC. And PGI has been one of the drivers for getting OpenACC standardized and bringing it alive and making GPU computing possible like that. When you leave this workshop here and you want to continue with OpenACC development and you don't have a compiler available, say on your laptop or something, you can go and just download the PGI Community Edition for free from our webpage. It's a fully functional compiler suite. The only difference with our other product lines are the support is only through the user forums, and there are only 2 or 1 update a year. So it's less frequent than the other ones. But otherwise, it's a fully functional OpenACC compiler, and you can use it on any platform that you like. Coming to the compilers themselves, I thought I'd add a few slides on how to use them pretty much as a reference sheet for you. Macro minus fast, for example, expands into. Okay? When you want to build a program for GPUs, essentially you have to add a -ACC, and then you will all the OpenACC directives will be translated, and GPU code will be generated. There is an additional flag that you probably have to use, which is -TA, which tells the compiler for what kind of architecture you're trying to generate code. So for example, you could specify Tesla here for a GPU, and then there are sub-options that will tell the compiler what compute capability you're using. For example, if you use CC60, you get code for Pascal, and all the specific hardware things will be utilized that are on that architecture. If you're working on a, say, K20, then you would use CC35 and things like that. Similarly, you can specify which CUDA version you want to use for the code generation. Yeah?
Which one is Daint?
Daint is CC60. It's this one. That's Pascal. Similar for the CUDA version, you can specify which CUDA version you want to generate, you want to use for generating code. And then there are also other options, including this one, multi-core. That one is interesting in the sense that the compiler will use your if you're working on a Cray machine like Daint here at CSCS, then there's usually a programming environment module that you load, and then you get the compiler. You get some default version loaded through this, but you can check what other versions are available, and you can load another version. And then if you want to generate code for the GPU, you will also have to load a Cray PEXL NVIDIA module. And the XX here stands for the compute capability of the GPU that you're using. 6.0 for Pascal, for example, on Daint here. If you have that loaded, then the usual wrappers will point to the PGI compilers. If you're working on some other machine or you need to invoke the compilers directly themselves, these are the commands for them. Some useful flags are -fast gives you sort of a usually comprehensive set of optimizations for the given architecture that you're working on at that time. And another very useful flag is -minfo, which switches on compiler diagnostics. So the compiler will tell you what kind of code it generated and will tell you about problems that, for example, prevented parallelization of a given loop or give you hints how you can solve certain problems. So it's a very useful thing to check the output of the compiler, in particular when you're generating GPU code. And you can use that in an iterative way. If you want to find out things for like what does -fast mean, for example, on a given architecture that you're working on, then you can always use the compiler with -help and then the other option, and it will tell you what this OpenACC directives to generate parallel code, but the target platform for which it will do so is the multi-core CPU. So you get parallel code from an OpenACC source code and OpenACC directives that will execute on your multi-core CPU instead of the GPU. One question in that context is, of course, yeah, go ahead, Markus.
How does that perform? Is it just for debugging, or is it really for...
No, thank you. I was about to, that was about what I was to say. The question is, of course, what do you get if you do that? And I'll show you. This is a comparison of some of the benchmarks in the Spec Excel. It's sort of a benchmark suite for accelerators. And what you see here are 3 different benchmarks. They have been compiled with Intel's OpenMP compiler for an Intel chip for Haswell. Then they have been compiled with PGI using the OpenACC directive. Some of these benchmarks have OpenMP and OpenACC. And we've used the TA equals multicore, like I just showed you, to generate parallel code for the multicore CPU. And then we've used OpenACC in a traditional way to generate code for a GPU. And this is the result that you get. You see that pretty much the baseline here is a performance on 1 core. It's sort of a skewed comparison. Usually for GPUs, you would do a socket-to-socket comparison. But because we need some baseline that also works for the speed up on the CPU, we're comparing it to 1 core.